Welcome, my dear children. Now we are going to introduce a problem, which is so even though it is previously asked, we have to see how the questions are explained based on the concept involved. Here the problem is a particle of mass m and a positive charge q moving with a constant velocity for I meter per second, and there is a region of uniform static magnetic field normal to the XY plane. The region of the magnetic field extends from x is equal to 0 to x is equal to L for all values of y. After passing through this region, the particle emerges on the other side after 10 milliseconds with the velocity u2 is given by equal to 2 into root 3I plus 2j meter per second. The correct statements are, we are given the statements, and you have to see that which one is correct and what are the correct options there. A particle of mass m and a positive charge q moving and enter into a region of uniform magnetic field normal to the XY plane. Now the plane of the body is our XY plane. This is X and this is Y, and this is our XY plane. And a magnetic field is normal. Normal means it can be either positive z direction or negative z direction. So this is z direction plus outward. Inward is negative z direction. Our magnetic field and existing there can be either inward or outward, the plane of the board, or it is in the positive z direction or negative z direction. And up to where the magnetic field existing, they told that is exists up to x is equal to L for any value y. So it will extend along the y direction up to infinity, but along the x direction it is limited region, that is equal to x is equal to L. For all of it, after passing through the region, the particle emerges the other side after 10 seconds, after 10 milliseconds, with the velocity u2 is equal to 2 root 2I plus j meter per second. Then the correct statement. So we can do, suppose this is x and this is our y, and here inward or outward there is magnetic field, and when the particle enter into with the velocity 4I, that is along the x direction, after some time, and the time of journey it is given 10 milliseconds, it is said that the particle emerge out from the magnetic field with the velocity to root 3I plus t velocity. And there you can see that velocity components, when it emerge out of the magnetic field, both are positive direction. It has got x component positive 2 root 3I, and y component is equal to 2j, and both velocity component uxi and uyj of the particle when it come out both positive, and hence before that, since it is perpendicular to magnetic field, it will take up a circular path because it's charged particle. A particle mass with a positive charge definitely take the curved path. Due to that curved motion, the particle must gain positive x component and y component velocity mean definitely the particle must be somewhere here in this quadrant, and the path must be, therefore, since initially it is along the x direction, the path must be definitely like this. This is the path, and suppose this is our L. Suppose this is our L. Suppose this is our L, up to which magnetic field is there. the particle take a curved path. And it emerges out of the magnetic field like this. With the velocity which has got x component here, Vx we can say. Vx is there is given by 2 root 3 I. And Vy there, this is a region where the magnetic field. And therefore, Vy here is given by 2g. Wait a second. And therefore, this is the way it went out. So, this is the resultant velocity there. And since it took up a positive charge particle took up a path like this, at once we can see what will be the direction of the magnetic field existing there. The particle projected, since perpendicular to magnetic field, it will take up a curved path with the field as the axis. Field as the axis. And therefore, the field as the axis means in which direction? This is the way it is rotating. And since it is rotating, the center of curvature must be somewhere here. Since a positive charge particle is there. And to have that situation, definitely the magnetic field must be along into the plane of the board, that is along the negative z direction. Then only the particle will take a curved path like this. If it is outward, the particle will take a path like this. But here it is like this, and therefore the first option is there. The direction of our first aim, in which the direction the magnetic field existing. With the field as the axis, the particle must take a curved path. And you can see that direction of the magnetic field is along the negative z direction. So this option is correct. Existing magnetic field. You can apply Fleming's rule if you want for finger field. Middle finger, the motion of the positive charge. Thumb represents the force. If you apply that, you can get the same result. Lorentz force equation, if you apply, you can get the same result. Next. Now come to back. It is one option that you obtain the direction of the magnetic field existing is in the inverted direction into the plane of the board, therefore negative z direction. But now the magnetic field we have to calculate. To get the strength of the magnetic field existing there, you can say, suppose this angle is equal to theta. If you draw this radius of curvature, this is the radius of curvature of the curved path that is going to be taken by this particle, radius of curvature. This is the center of curvature of the path is just going to take up. If you draw the tangent, this is theta. Then what is tan theta? Tan theta is gone by. Tan theta is gone by tan theta. Here you can see that y component by x component of velocity, that is equal to 2 by 2 root 3. So 1 by root 3. Therefore, theta is given as 1 by root 3, pi by 6, 30 degree. So this angle, here you know that this angle theta is equal to pi by 6. Then what about this angle? Pi by 6. If this is pi by 6, if this angle is pi by 6, this angle is also pi by 6. Therefore, our particle during a time that is given in the problem, that is 10 milliseconds, now turned through an angle pi by 6. Therefore, you can calculate what is the angular speed, the average angular speed of that particle. Angular speed of this particle omega is given by angle by time. Angle is equal to pi by 6 by time taken to emerge out, the time taken by the particle to emerge out this existing magnetic field. Emerge out from the existing magnetic field is 10 milliseconds. So it's equal to 10 into 10 raised to minus 3. So much radian per second. This is our omega. But when a particle, when take up a circular path in a magnetic field, when it travels perpendicular to a magnetic field, you know the value of the radius equation. R is given by mv by bq. From this, omega is equal to v by r. Omega is equal to v by r is given by bq by m. Omega is equal to bq by m from here. Bq by m is equal to v by r is equal to omega. Now omega you got bq by m. Now substituting here for omega in this equation. Substituting omega in this equation, you get bq by m is equal to pi by 60 into 10 raised to minus 3. And what is asked there? We have to calculate the amount of the magnetic field. Direction of the magnetic field already got. Now the strength of the magnetic field B is given by B is equal to pi m by q into 60 into 10 raised to minus 3. Capital M, instead we use a small m, this okay. Q itself, capital Q is there. Now you can see this can be written as 10 raised to 3 pi capital M I am using by capital Q into 60. This on calculation is equal to 100 by 6, 50 by 2. 100 by 6, 50 by 3. 50 by 3 pi m by q. This is the magnetic field existing there. 50 pi m by 3q. So that option is there. But this is wrong, this is wrong. Now, the concept applied in this problem very clear. The Lorentz magnetic force, again when I charge the particle projected perpendicular. Yes, thank you. See you in next class.